All right. Hello, everybody. Welcome to our sixth BRR training session on reinforced concrete slab bridges in BRR. I don't have much to start us off with, so I'll hand it off right to Pro Miles. Thanks, everybody.
Thanks, John. All right. Okay, so again, my name's Carolyn. We've also got Mark here from Pro Miles. Jeff's going to be on the call here as well. Today we are going to be covering the creation of reinforced concrete slab bridges. So let me share my screen.
And as always, if you have any questions while Carolyn is going along, please just put them in the chat and we will get to them as soon as we can.
Yes, thank you. Yeah. And again, as we're going through this, I would encourage you all to follow along. We have the training licenses that are available that were sent out a couple weeks ago. And like Mark said, we want to make sure we answer all the questions. So go ahead and put those in the chat. All right. So So this is the third structure type that we're going to be covering here as far as creating a new one from scratch. In the first few trainings, we talked about using the template bridges. So for this one, we're going to do reinforced concrete slab. And we'll be creating this as a new structure. The tutorial for this was included in the email that was sent out a little while back. So this is the RC6 two-span reinforced concrete slab system. So again, I think you'll see as we go through this, there are a number of things with this structure type that are going to be similar or consistent with the last two structures that we did, the steel and pre-stress. There are some differences here, and we'll be going through all of that. But the first couple of pages here, we have some information about the structure that we're going to be modeling. So this is a two-span concrete slab with a like parabolic depth variation along the slab. And then we have some information here on material properties and dimensions. All right, so, okay. All right, so to get started, we're going to create a new bridge. Same way as we did the last ones, just click the new button here. And we will start out just by setting up the structure definition. And again, we can uncheck culverts since we are not going to be using that, and that'll just take that out of the bridge tree here. All right, similarly to the other bridge types, you'll also want to populate the relevant fields here in these other tabs. So county, location, as well as the custom agency fields. So we've got this filled out. We can go ahead and click. Basically, it's telling me the structure ID that I typed in here is not unique. So it will require you to put in unique structure number. Okay. And again, we can always get back to that window just by clicking at the top of the bridge tree here. All right, so we'll start out by creating the materials that we're going to use for this bridge. And so we'll define the concrete here, and we can copy this from the library. So we go to copy from library, and we have this Class A for KSI. Again, we can review all the properties here. If you do want to use a library material and just update like for a different strength, you can always just copy in the library material, change the compressive strength or other properties up here, and then use the compute button to recompute these other values. And then that'll save basically a modified copy of that library item to the individual bridge that you're working in. But for this example, we can use the library material without modifications. So I'll go ahead and click OK, and that adds the concrete material. So we're going to do the same thing for reinforcing steel, and copy from library. And we'll select the grade 60. Review the properties and save it to the bridge tree. And then we're also going to add parapets. So I'll go to appurtenances and parapet. And we will enter the information for this parapet here. Again, keep in mind the standard appurtenances for the template models are included in the Iowa DOT library files. So be sure to check those library items for the common appurtenance types. All right, so we've added parapet shape. So that is all the components that we're going to need for this bridge type. So we can switch back over to the bridge tab. We see the components there that we just defined. And we can go ahead and create a new superstructure definition. So we'll just double click superstructure definitions, and then we see our different superstructure options here. The last two that we did were both girder system superstructures, the steel and the pre-stressed concrete. For this one, we're going to select reinforced concrete slab system superstructure and go ahead and click OK. And then we will just populate the superstructure definition tab here. So for this bridge, we'll go ahead and set up the spans, and then you'll see that it's asking for a number of slab strips. For this example, we're going to be modeling 3 slab strips. So we'll have like an interior section, and then we'll have an exterior slab strip on each side. And we can talk a little bit more about that as we go through the example. Again, you'll see some different analysis options here, as well as specifications. Like these should be populated. Yeah, so Normally these should be automatically populated by default when you go to this window. I put them in there right now just because they were not for this bridge. But we can go ahead and click OK. And then again, we can get back to that window here just by double clicking for this superstructure definition. All right, so once we set up the superstructure, we're going to go ahead and create a bridge alternative. This is the same thing that we did for the last two structure types, the same process. Again, this is important just because it tells the software what it needs to analyze when you're running a batch analysis or running a rating from the Bridge Explorer. So we'll just take a minute and go ahead and create the bridge alternative here. And then we just expand that and add the superstructure. And then select the superstructure that we want included. Again, you'll see in some cases where if you have different superstructures the same um, within the same bridge model, you can assign multiple structures here so that they're all included in the analysis and select the ones that should be included. All right, so we've got our bridge alternative set up. Um, okay, so we got our bridge alternative set up, and then let's see if we go back here, we can see as well that defaults to the alternative that's selected here. So that looks good. All right, so going back to our superstructure definition. So we have our slab system. We don't need to modify anything in the impact dynamic load allowance window. This is just going to default to AASHTO standard impact. So the first thing we'll do is create the load case description here. So we're just going to add one for the parapets. The loads for like the structure itself, the slab, are generated by the program. So this is basically where we're creating load cases for appurtenances or member loads, like any other added loads aside from what's modeled. It's non-composite. Um, so we can go ahead and click OK, and we've got our load case descriptions defined. All right, so moving on to the framing plan detail. All right, so like I mentioned, when we're setting up the superstructure definition, we set this up so that there are going to be 3 slab strips for analysis in this structure. So for the example, the width of the edge strips is going to be 7.5 feet, and then the interior one will be 12 feet. So basically, the center the center to center strip spacing that we're entering here on the framing plan should be the center to center of those slab strips. Similarly to like a girder system, this is just the spacing between the center lines of those different sections that are going to be modeled. Okay. And again, we should be able to see schematics here as we get this populated. So the next thing that we will do is set up the structure typical section. Again, this is going to be very similar to the other structure types. A little bit different here for the slab, but so we've got the distance from the left edge of deck to the reference line, and then the right edge, and then the half strip width. So like for a girder system, you would see like over here, you would see the overhang. For slab, it's the half strip width for the left strip. You have a few things here. This example, I don't believe we need to enter anything in this window, but for concrete slab, you do have some additional things here in the deck tab. So we will go ahead and set up the parapets on the structure. So we've got the parapets, the load cases, and the geometry. So once that is set up, we don't have any of these other appurtenances for this one, so we can go ahead over to lane position. And since we have the deck width already defined here in this first tab and the parapet positions defined here, in this tab, the program now has enough information to compute the travel way in between the appurtenances. So we can click the compute button. It'll give us the computed values, and we can click apply. Again, these also can just be entered manually. If for some reason you had a structure where you wanted to, you had something that is going to be something other than just the distance between those barriers. Right. So I think that's all we've got for the structure typical section tab. So I can go ahead and click OK and pull up the schematic. So, so you'll see, again, this looks a little different than some of the other ones, but kind of similar concepts. So we've got the travelway, we've got the parapet locations. This is just showing generic shapes here since we don't have the actual slab members set up yet. Again, this is kind of similar to the girder system structure, where it's basically measuring the distance here to the middle of the exterior slab, and then to the middle of the center slab, and then the other one. And so then this will get populated once we create the members. Sorry, sorry, I think we have a question here. Just give me 1 second.
We do. Can you go over how you determine what your slab widths were? Were they based upon reinforcing patterns, e.g. usually beneath the barrier edge of deck has a different pattern than elsewhere?
Yeah, so let me just pull pull this back up here. Yeah. Okay. Yeah. So for this bridge, we have, just kind of the limited details that are shown at the beginning of the example. But there would be, I guess, potentially some different things would want to take into consideration for that. So the AASHTO LRFD distribution factors, I think, are different for exterior or interior sections. So that would be, I guess, one consideration, just to review the AASHTO stuff with that. But then, like you mentioned as well, sometimes you will have structures that have different reinforcing patterns at like the edge of the slab. And so we'll kind of take a look at a couple of things in here when we go to create the members as far as like the reinforcement and the live load distribution. But I guess in short, the program so I guess actually I want to take a step back here. So for the reinforced concrete slab structures, the software currently does like a line model analysis. So it's not doing a 3D finite element slab. Like we talked about, the girder systems will do that. So it is performing a line analysis, based on each of these sections. Now, when you look at the different widths, basically the software will you should be able to define those widths differently and come up with more or less the same results in a lot of cases. So for example, if you have an interior strip that's 2 feet wide or 10 feet wide or whatever, the dead load should correspond to that width, and then the live load as well, in the sense that the software will use the AASHTO distribution factors to calculate that load distribution and then take the proportion of that that's applicable to that width, and go from there. The couple of things to keep in mind are, when you enter the reinforcement, it is for that width. So you want to be careful about that. And then, like I said, there is some stuff in the LRFR spec that relates to, I think, load distribution on exterior strips. Does that kind of make sense? Or I don't know, Mark, did you want to add anything to that?
No, I think that's a good explanation. So basically, if you have and this isn't the case, but if you had exactly the same spacing the entire width of the structure, then it's going to give you roughly the same answer no matter how many sections you divide it into. You do have different spacing at the exterior girders, and so you may want to consider doing different spacings there. Again, a lot of this is engineering judgment. We don't really have guidelines. It depends on the cross section that you have and decisions that you make with the DOT that you're working for. So it's every structure is different, and you can use this if you have variations in your spacing as you move across the typical section. I don't know if that helps or not.
Yeah, I'm glad you mentioned that. I think that's a good way to sum it up, is basically the different strips that you have are you would make them different because there's a difference between them that you'd want to analyze differently. So it would usually be either different reinforcement towards the edge of the slab, or for LRFD, different live load distribution. So, but yeah,
Correct.
Yeah. Okay. And yeah, we'll show a little bit more with the input on this as we go through it. But if there are other questions about this or anything, please follow up, let us know here in the chat. And we'll do the best we can to address any other questions or any other follow-up questions on this. But so yeah, and I guess just to, as it sort of relates to that, like I said, looking at this schematic, this is sort of keeping within the way that that BrR like sort of shows these things. So right now it's just showing generic shape here, but really once we get those members populated, it's the 3 different slab strips. It's just that there may be differences in capacity or live load factors between the three. So, all right. So let's see, we've got our structure typical section set up there. And then let's see, we don't need to make any changes with superstructure loads. So the next thing that we'll do is go ahead and create the bar mark definitions that we'll be using for this structure. I think we've only got 2 different bars here, and we'll yeah, so basically we're defining 2 different bar types, and then later when we get into the member alternative, we'll be positioning them within the girder. And so we'll show a few things there as far as how you set those up. If you remember, when we were looking at the structure kind of profile at the beginning, this is a variable depth, like there is a parabolic depth variation. And so we're gonna just define these couple of straight bars here, but you'll see how they get assigned to the structure once we get into the member type. Okay. All right, so we've got the bar marks set up there, and we'll be able to use those in the structure. For this example, we're going to go ahead and start out with creating the interior strip. The exterior strips are going to be created basically the same way, but for this example, we're going to do the interior strip here. So we can just double click member alternatives. Our only options here are reinforced concrete slab. That's just because that's specific to this superstructure definition. So we can click OK. And just get the member alternative window set up here. All right, so we've got the description, and then these tabs again are going to be very similar to the other structure types we've looked at. We have different spec versions that you can select for analysis in the event that you want to compare factors here. And control options. And again, the control options are going to be different for each structure type. So whenever you're creating a new bridge from scratch, you'll definitely want to review these control options and make sure that you're selecting the ones that are appropriate for that structure and for the analysis that you're running. So, all right, so we've got the member alternative populated here. And then it'll create these options here now. One other thing just to point out as well, so this is the interior strip that we defined here. For the exterior strips, you'll just want to check this edge beam check in the member alternative description so that if you're running LRFR, computes the appropriate distribution factors. All right, so again, we don't need to make any changes for default materials or impact dynamic load allowance. So we will go ahead and create the strip profile. All right, so this is the two span bridge. So we're saying that this is going to span, the entire length of the bridge over the two spans. And then we've got the width here that corresponds with the slab strip width that we set up in the framing plan and typical section. Modular ratio, again, it is be computed if it's not entered. And then we just created the one concrete material. If you have different ones, just make sure to select the one the right one there. Um, So this is where we set up the width. Then we can go over here to depth, and then this is where we'll set up the depth variation. Um, so we'll take a minute to get this set up here. So one thing to keep in mind when you're setting this up is just, I guess, pay attention to the beginning and end depth as well as like the depth variation. So this is saying for the first section, this 20 feet section, this is going to be straight. And then at the beginning of this next section here, it'll start at that same depth and then um, vary here parabolically. And so then when we select depth variation, um, this field here for end depth becomes enabled and we can create a different end depth for that section. And then you'll notice too, as you're going through the table, if when you start with the first one, it'll pick up that end distance and length and update here. Keep an eye on that too. All right, so this is defining the profile of the beam. There is a schematic for this that we'll be able to look at a little bit later. You can always use that to verify um, that you got your dimensions the way that you want them here. Now, the next thing in this tab is the reinforcement. So earlier we had created two bar mark definitions, and what we'll be doing here is assigning them to the slab. I'm going to go ahead and um, I'm going to go ahead and click OK here so that I can open up the schematic, and then we'll come back and look at the reinforcement. So we'll click OK. That populates this strip here in the cross-section schematic, but then we should be able to see the profile here. Yes. Okay. So once we've created that strip profile here, you can right click on the member alternative, go to schematic, and it'll pull up the profile view of that slab that we created there. So, all right, going back into strip profile to do the reinforcement. All right, so the reason that I wanted to pull this up was just to point out here as far as this measured from field. So when we created those bars, you have a few different options for reinforcing. Sorry, I'm gonna get one more window open here real quick. All right, so we've got a few different bar types that you can create here. So you've got, straight and hooked, and then you've got a few different types of bent bars. So if you have one of these types of bars that's a bent bar, you have the checkbox here in the reinforcement tab to invert that bar. So you can flip those around. And then you also have this measured from top of slab or bottom of slab. So For this one, some of these bars will be defining, we have straight bars defined, we'll be measuring from the top of slab, and then the other ones will be measuring from bottom of slab. And so that'll allow them to basically follow that profile. So, all right, so let's take a minute and get these reinforcement bars entered here. And then you also have checkboxes here for start and end fully developed. If you don't check those, the program will look at development length and account for that in the sections where the bar is partially developed at the ends. All right, so the one other thing just to note here. So we had talked a little bit before just about the strip width. So like we had said, you can set those strip widths to, you know, different widths, and the program will account for the dead load and the live load accordingly, like we were talking about earlier. But the reinforcement, the section width and the reinforcement that you're entering here is for that section width. So if you're creating a model and then for whatever reason you decide you want to change that strip width, just keep in mind that you'll need to make sure that this matches up with it. As long as the reinforcement is proportioned, the reinforcement that's entered here is proportional to the width of the strip that you're modeling. You should, for the most part, get the same results if you do use different strip widths. So just wanted to point that out, is that this is based on the width of that slab. All right, so you can go ahead and click OK. All right, and then like I said, you can get to this schematic here, just right-clicking the member alternative schematic, again, just to verify that your profile looks the way that you want it to. Okay, so for this structure, we don't need to do anything with effective supports or hinges. We will go into the live load distribution window here. And we'll do compute from typical section. And we can go to view calcs. So again, that view calcs button will open up this window that'll show you how that load distribution is computed. Again, if you leave that blank, it'll compute those distribution factors at runtime. But to be able to and you can pull that report up, when you run the analysis at the end too. But if you want to, again, compute and save, or for some reason override what would be computed, you can go ahead and enter those values there. So this is another thing where we can review where it's taking the strip width, it's computing the load distribution width, and then when it runs the analysis, it'll look at that loading proportionally to the width of the strip that's entered. And that's also same thing for the LRFR. You can compute and view these as well. This example just has the LFR, but you've got all the LRFR version of it in here as well. Actually, maybe I should have saved that. Nope, we're good. Okay. And then let's see. And then yeah, then we've got another points of interest window here. Again, we talked about this a little bit before with some of the other structure types and then also with templates, but there are some options here to override some different things in the event that you need to for capacity reductions for deterioration or things like that. You can use points of interest to do that. All right, so we've got that defined. Again, it would be a similar, process to define these two exterior as well. And again, but we can go ahead and run the analysis here. So for this one, we'll do the LFR, HS20 LFR rating. Again, the Iowa DOT libraries include different analysis templates for that. This is just for this example. We're just looking at the design vehicle rating. Okay. So then with that member alternative selected, we can go ahead and click Analyze. And we'll see the analysis progress here. So again, similarly with other structure types, you'll see analysis progress and info, as well as any errors or warnings will come up here. Again, some of these warnings are basically just saying that different things are not entered and either will be computed by the program or are not included. All right, so we can go to tabular results. Same for other structure types. Okay, so okay, this is showing up slightly different than the example. I may have entered something. I may have been a little off with something that I had entered. So this is showing slightly different results than the example. So for this, you can basically open up tabular results and you'll see, your rating factor as well as controlling location and span and the limit state. And then, like with the other structure types, you've got your spec check detail that will give you the additional spec check output here, so you can review the loads and everything that's going into that rating. If you are running LRFR and you want to see and you want to review the in-depth spec check, you'll just want to go and make sure that this checkbox here is checked for when you do LRFR and output. So if you're running an analysis and you want to generate all that output, I'll just run one of those just real quick. to show. And you'll see for this, for the LRFR for concrete structures, it does generate a lot of output, and there is, you know, quite a bit of stuff, which is why that's not default checked, because you don't necessarily want to do that every time you run the analysis. Just wanted to point out that it's, you know, if you want to be able to, you want to make sure you want to be able to open up those spec articles, you'll just want to turn that on. And so you'll have all of those results here too. And then in engine outputs, we have a few different things here. Again, the different things and reports that you'll see in engine outputs are different for different structure types. So for this one, you can see the distribution factor calculations. You can also review the development length calculations. And for this structure, we had said those reinforcement are fully developed, but for a structure where you did want to, you know, you did want to account for all of that, you've got development length calculations there. And then live load distribution for LFR and everything as well. And I just ran the LFR here, so we've got the spec check results for the analysis that I just ran. One other thing to mention, so for concrete slabs, you know, a lot of times you're not going to really have shear control, which is why we didn't have distribution factors in there, and where we didn't see that's why in this report it said ignored by user, ignored by user for shear. To change things like that, if for some reason you did want to look at that, you could just come into the control options. And again, you know, anytime you're modeling a new structure from scratch, it is really important to review those control options and just make sure that it's checking the things that you want it to check, and it's doing it the way, and it's, you know, using the analysis option that you want it to use. All right, so that covers the creation of the concrete slab structure. Again, the software analyzes this as like a 2D finite element analysis. So when you're creating one of these structures, you would, you know, basically create, in addition, you would just do the exterior strips as well. This example doesn't include like reinforcement information for the different width on those. But just keep in mind, it will analyze each one as like a 2D, like line girder type of analysis, or line structure, I guess, type of analysis. Again, you can copy, paste, and modify, same as you can with girder structures. So, you know, that should be, you know, you go ahead and do that. Now, there is a second part of this example that kind of talks about the simplified frame structure definition. I guess we can take a minute and discuss that. It's probably not going to be super commonly used, but it is there, and so we can go over it and take a look at it. But I guess before we get to that, I wanted to see if there are any questions on what we've covered so far. Let me just try.
We do have a question regarding the end bearing location input.
Let me look here. Quick question regarding end bearing location input within the member alternative does not appear to affect the results. It seems to be conservative, analyzing the full length of the bridge rather than the clear span between bearings, Okay, so that's a good question. I think there's a few things here. If I'm, I guess, reading this correctly, I think there's a few things. So there's this end bearing locations here in the member alternative. And that should be in here, end bearing locations. Yeah, so the end bearing location is basically just center line of bearing to the end of the actual member. So what BRR is looking at in terms of dimensions and everything, when you set up the system, the span lengths that you're using here, this is basically going to be the center to center of bearing. So yeah, center to center of bearing. And then the end bearing location is just that center of bearing to the end of the beam. So for the concrete slab type structure, you're right. I don't believe would make a difference in the rating as far as what you're modeling over here for this particular type of a structure. When you look at things like the pre-stress I-beam bridges that we talked about like in the last training, for those this information is used to look at the offset between different beams when you make a structure continuous for live load. So that information is used there. And then additionally, when you set up the span length as center to center bearing, when you go to enter the reinforcement, the plans that you're going to be looking at are usually are always going to show, the actual reinforcement in the beam, including these end parts. So for this structure, having this end bearing here, for this structure, doesn't, I don't think would make a difference in the analysis, but when you're going to input your reinforcement, it can get really confusing if you don't have that there. There's one other thing about this that I was thinking of that I forgot now. Hold on a second. Students seems to be conservative, analyzing the full length of the bridge rather than the clear span between bearings. Right. Okay. So yeah. So like I said, so it when it looks at spans, it is the center to center bearings. I know there is one other thing. So like I said, this can be helpful when you're setting up just so that you get the actual full length of the member itself for the reinforcement. But then the other thing there is too is there's this effective supports window. Um, and let me just see here. So this does give you some options on if you wanted to, I guess, make some adjustments for different like structure types. I honestly haven't used this all that often, but this does have some additional ways that you can like kind of specify face of support. Um,
Yeah, and some of this has to do with where shear gets evaluated as well, like
Right.
where the critical distance is located.
right. And yeah, and so I guess all these things kind of tie together here. I guess in the sense of just making sure that for each of these things to make sure that you know what the program is looking for. So like we said here, we have this like face of support and stuff, which like Mark said is used for shear and things like that. Um, and then the spans, whoops, the spans that are defined in here in the system definition, this is like center to center bearing. And then, like we said, here in the member alternative, these end bearing locations or offsets is just that distance from that center of bearing back towards the end of the beam. And so like we said, this doesn't really make a difference for this bridge type other than just the ability to get reinforcement lined up correctly. It is important for things like I said with pre-stress where you have multi-span bridge that's single span for dead load made continuous for live load.
Yeah, and I guess for the and it doesn't really apply to this case, but for pre-stressed girders that distance from the end of the beam to the bearing is critical because the pre-stressing is measured from the end of the beam. And so your development length for the um, for the pre-stressing is measured from there. And I guess that's true for the reinforcement as well.
Yeah, that's a good point. I didn't think of that. Yeah, on this one, we have uh, the boxes checked for like consider fully developed, but yeah, you're absolutely right. That definitely will make a difference.
You're welcome. Hopefully that fully answers your question, Braden, but if you have any follow-ups, let us know.
Yeah, for sure. All right. Do we have any other questions before we take a look at this next part? I don't think we do. Okay. All right. So, like I said, this next part here is probably not going to be very commonly used. We do have it in here again. If you're creating a bridge from scratch, it may be because you run across a bridge that has different things where you might want to consider this. So um, the the last part of this tutorial kind of is sort of a brief overview of the frame structure simplified definition. Um, so this bridge, this like example bridge itself, here's what I'm going to do. I think this will work. All right, I'm going to copy this superstructure definition just in case I mess something up here as I'm going through and changing things. But I went ahead and made a copy of this so we can take a look at what happens if we select a different slab structure type. I think it'll let me change this. We'll see. We'll see as we go along. But so I opened back up the superstructure definition window. I'll just minimize this one. So I open up the superstructure definition window. And this is, like I said, this is a copy of the bridge we just made. And so here we have slab not integral with pier was the way that we modeled that one. So this is basically just looking at, the slab with the variable depth, but sitting on top of a bearing here. If we switch over to frame structure simplified definition for the slab structure type, you'll see this will come up here. You'll have this window for frame connections. So we can go ahead and select this middle one, and this is basically telling the software, hey, this is not just sitting on top of the bearing. We do actually have a frame connection there. Now the tutorial says to go through and recreate the structure. We're not going to do that for the sake of time, but I think I should be able to make this change here and just briefly demo making this change. We'll see. Okay. All right, so we went in here and yes, set slab structure type to frame structure, simplified definition. Now, all the rest of this should stay the same, but there's a couple things we're going to want to look at. So the first thing is we'll go into the framing plan detail. And you'll see we now have this frame connections tab. So this wasn't here before. This just becomes enabled when you select frame structure simplified definition. So what this is going to do is this is going to allow you to put in some information about the frame element that is that this superstructure is connected to, so that it can get basically the stiffness for that support. So it's not going to actually analyze like the vertical element of the frame, but the purpose of this is to get like the stiffness of that connection for the slab. So if we enter some info here about this cap and columns, percent fixity at base. So we've got cap width, columns, material, column length, fixity at base, column type, and then column geometry and dimensions. Okay. Once we have this information entered, I think we should be able to, yes. Okay, once we have this information entered, and then we go over to this window here, this compute button is enabled, and this will allow us to compute this column stiffness per girder. So, oops. Okay. So yeah, so this basically gets this information about the column cross sections and computes a column stiffness from that information. And then you can go ahead and click apply, and it'll save this here. So again, this is something that, you know, is probably not going to be too frequently used, and it will be important to, you know, kind of look, you know, there is, I think, some kind of engineering judgment that comes in as far as exactly how you want to model all of this. I mean, even when you get into things like percent fixity at base, things like that, you will just want to make sure that that it makes sense for whatever structure you're modeling. But if you you know, if you enter that, then what it will do is it'll account for that stiffness. So then we can go back and just review the supports for the member that we had here. Okay, so we have pinned and roller, and then we see that the second support changed to frame connection, and so this is then we have translation and rotation constraints, and then in the elastic it populates this rotation spring constant that was computed in that framing plan window. So then we can rerun the analysis same way as we did before, and this will just account for the stiffness of that member. Where this template came from. Yeah, so this, you know, this will run the analysis, accounting for, you know, different stiffness within that support. Let me just see if there's anything else with this. Right, I think that covers it. See here, are there any other questions or anything? And I'm not seeing any questions on the chat here.
Yeah, I think we're all caught up there.
Hey, Carolyn, I just want to jump in.
Sure.
Just one thing you'll notice with the slab templates is that we decided to go the full strip, or the full width of the bridge. You can go with the 12-inch strip method if you guys want, and I don't know, Carolyn, if you want to go with, maybe talk about pros and cons of the two options.
Oh, sure.
But so if you don't want to go with the full strip width and you just want to do that 12-inch strip, that is a possibility. We decided not to do that with the slab templates. I think we were trying to future-proof them as much as we possibly could, so we went the full width. But I just wanted to add that in there.
Yeah, thank you, Sean. Yeah, so there are a few different ways that you can do the slabs in BRR. I mean, with this, where we set up that the full width, like we were talking about here earlier with the strips over the full width. When you run it with the full width, like we were saying, it does look at the proportion of the dead load, the proportion of the live load that should be applied, to that width. And so, you should be able to get the same results if you did want to just do a 1 foot strip width. As of right now, like we said, the software does not do a full 3D analysis for slab, but it's possible. I mean, it's definitely possible that could be added in the future. And then again, when you do that full width, you also do have the option to position, you could do different vehicle positioning. Again, it's probably going to be really uncommon for a slab where you would need to say, okay, well, let's, try and make sure this is positioned in the exact place. But modeling the full width of the structure, like Sean said, does help in terms of just trying to make the structure as complete as possible. So that as other capabilities and things are added in the future, it matches up with what's there.
And to add on to that, Sean, you mentioned future proofing. Once these structures are entered, they may be used for the next 20, 30, 40 years. It's a new bridge. It could be longer than that. And so when the an example is when the girder system was first introduced into BRR in the early 2000s, most states started inputting them as an entire girder system rather than just a line girder. At that time, there was no capability for 3D analysis of multi-girder systems in BRR. When that was added later, all of those structures with very little change were able to be analyzed in 3D if needed. Typically, it's not needed, but if you have special permit vehicles, you may need to do that. So this is analogous to the multi-girder system, where even though that capability isn't there now, it may be there in the future. So you really want to do the best to describe the entire structure.
Yes. Yeah. Thank you, Mark. All right. I'm not seeing any other questions. Anyone had anything else? Just let us know. Yeah, well, I'm not seeing any questions now. If you all, whoops, sorry. If you all are working through the example here, and still working through it, I'll stay on here. So if you do come up with any questions, just let us know.
All right, everybody. I see a lot of people are dropping off. So if you guys do want to drop off, I'll let you guys go. But if you guys do want to stick around, we'll let us know and we'll stick around as well if you have any questions. So thanks, everybody.
Thank you all.
Thank you.